So now assume that we have two random variables and we want to know how we can calculate the joint moment, how we define them, and so on. So joint moment, if you have two random variables x and y, basically if you define any function of them, g of x and y is defined by the expected value of this function. So we call it a joint moment or a joint behavior or joint statistic. So joint moment is basically defined as using a function as the following expected value. So because we have many different possible functions, then you could define various possible joint moments. So the expected value of this function is summation or integral over all possible values that x and y can take. So here this means integral over x from minus infinity to plus infinity, and integral from minus infinity to plus infinity of, let's say the outer integral is y and in integral is x. If your random variables are of discrete type, instead of integral you have sum, and then you put the value that these functions can take. The value of x goes here, g of x and y, and then you would put different weights of the PDF, fxy of x and y, and then dx dy. So expected value of this function is average of this function, and this average is weighted by the density of the probability. So obviously you could define different joint moments, and each of them has some properties. It tells you like that. For instance, one joint moment is mean of x, because this is a function of joint. Another one is mean of y. A third one is mean of x to the power of 2. Mean of y to the power of 2, or mean of x times y, or mean of x plus y. So these are all different joint moments of x and y. So if you define a random variable as a function of two random variables, then expected value of z is equal to the joint moment. So this is trivial. An important property of the joint moment is that if you have, let's say, 4 or 5 functions and then you multiply them by a scalar value, so let's say ak's are real number. That means that they are not random. And then if you multiply them, so let's say you put the first one by 2 and the second one by 3, and then you add them, you could say that this linearly property holds. So this is very easy to prove. Otherwise, this theorem says that you could put this expectation operation inside here. So the order of expectation and summation, and here the summation is applied, expectation is applied first and summation then, or you could apply the summation and then expectation. So the order of this is called linear combination. And expectation can be changed. This is true that it is trivial because expectation is a linear combination over your function using these weights. And linear combination is also a linear combination of these entities using these weights. So the order, so this is coming from the properties of the numbers. So as an example, in some cases, we have mean of xy is not equal to mean of x, mean of y. So this property, you cannot put this expectation inside the function and so on. So remember that. But there are examples that mean of xy is equal to that. So let's say, for instance, mean of xy is mean of x plus y is the average of x plus y over the PDF. So remember that this is equal to integral of x plus y, fxy of x and y, and then dx dy. So you have a double integral, and then x from minus infinity to plus infinity, and y is from minus infinity to plus infinity. So this averaging is over PDF, averaging over PDF. Now, you could do another averaging and take, like, realize these random variable in different experiment. And let's say the first experiment you get x of xc1 and then plus y of xc1. Then you could repeat this experiment and get x of xc2 plus y of xc2, and so on. And last one, you get x of xn plus y of xn. So another averaging is to do ensemble averaging. So the outcome of experiment, which is this one, and this one, so you have n of them, you add them together, and then you divide them by the total number of experiment, n. So this is called averaging over ensembles, or averaging over frequency, and so on. So if you increase this number of n, in many cases, in most cases in probability, if these guys are independent experiment, you would expect that these frequency averaging will converge to this one. So this is not all the time, so you need to have some properties. We learn it about these concepts in chapter 16 little bit, not in much detail. So what we see here is that if you do these averaging, this sum, the second, this side, you could add these all x's, group them together, so you will get x of c1 plus x of cn divided by n, and then you could put y is y of cn plus y of cn divided by n. And you see that this side you could do this frequency averaging, and this one is equal to mean of x plus mean of y. So this justifies that when we do expectation, this is a linear operation. However, if you so you could see that this is equal to this, and this is equal to that, and if n goes to infinity, this shall converge to this one, and this guy shall converge to this one, and this guy shall converge to this one. So we'll see that this matches. However, if you average over these, which should converge, this one should converge to this one, this is not equal to, right, I take the average of this one, I take the average of this one, I multiply them. Because when you multiply these together, you will get 1 over n2, and then you will get summation of, let's say, x of xi, and then y of xj, and you have a double sum I over I and over j, and I and j are not equal. So here you will get n2 terms, and then you have factor of n2, but here you don't have the same thing. So these two guys are not equal. So in general case, this is not equal to that. There are exceptional cases that this could happen. So these function mean of x, y, you cannot put it on each of them separately. So this equality is not correct in all cases. So it's correct in this case only.